Now let's look at this graph of the tangent function so that we can decide what we would need to restrict the domain of the tangent function to in order to be able to define an inverse function. Since the tangent function repeats itself every pi, if we simply use the values between negative pi over 2 and pi, then we will, for our domain of the tangent, then we will be able to have every possible value that we would get for the tangent of an angle inside of there. And that is not including the negative pi over 2 and pi over 2 because our tangent function is not defined at those two values. But all the values in between those two angles we would use to define this. And so our inverse tangent function, which is denoted in this way, is also the arctangent, is defined to be the inverse of the restricted tangent function when we're restricting our tangent function to run between negative pi over 2 and pi over 2. So inverse tangent of x is the angle, it's the number in the interval, the angle in the interval from negative pi over 2 to pi over 2 whose tangent is x. If we look at this graph over here, I want you to notice that the inverse tangent function is going to have a domain all the way from negative infinity to infinity. We can use any value on there because it continues in both directions. That was not the case for our sine and cosine function. But the inverse tangent function is also going to have a cancellation property when it works with the tangent function. So when we take tangent and plug in inverse tangent x, then we're going to get x. If we took an x that's anywhere in the real numbers. When we go the other direction, inverse tangent acting on tangent of x, we're going to get x as long as we were only plugging in a value between negative pi over 2 and pi over 2. So let's now work some problems that involve the inverse tangent of x. If we are trying to find the inverse tangent that gives us negative 1. So first of all, let's recall, since we're going between negative pi over 2 and pi over 2, that means we're dealing with quadrant 1 and quadrant 2. Quadrant 1 and quadrant 4. Our tangent values are positive in quadrant 1, we'll get negative ones down in quadrant 4. We're after an angle that gave us a negative tangent, that means it had to come from quadrant 4. Since it was between negative pi over 2 and pi over 2, and it gave us a negative tangent, then it must be in quadrant 4. And the angle down here in quadrant 4 that gives us negative 1 for the tangent, since tangent is sine over cosine, it's y over x, is going to be here in the middle. It's our negative pi over 4. In the middle of quadrant 4, that is. So negative pi over 4, that is since, so you can either show your work to me this way, or you can show it this way, since the tangent of negative pi over 4 is equal to negative 1. Alright, let's look at the angle whose tangent gives us the square root of 3. Here we have a positive value for our tangent, so we must have come from quadrant 1 when we're looking between negative pi over 2 and pi over 2 for our answer. And so we must have come from quadrant 1, and the angle that would give us the square root of 3 for that would then be pi over 3. And that is since the tangent of pi over 3 is equal to the square root of 3. Again, you can use your calculator to check these to make sure you're getting the right answer. So on a test, if we want to make sure we've got the right answer, we can say, okay, let me check that. If I take the tangent of pi over 3, I get this number. Well, what is the square root of 3? Well, the square root of 3 is the same number. So indeed, we got the right answer on that one. Let's look down here at the inverse tangent of 22. Now this one isn't going to be something we know from the unit circle, so we'll have to bring the calculator down for this one. Again, always make sure you've got it in the right mode, and we do this time. It's in radians. So we want to know what is the inverse tangent of 22. What's the angle that gave me a tangent of 22? Well, it's 1.525373, etc., etc. If we only want to go to 5 digits, we'll look at that 7 as where we end. Do we get bigger or not based on the 3? We don't. So this is going to be approximately, make sure you're using squiggly equal sign when it's not an exact answer. Up here, the rest of them were exact answers, but not on this one it's not, because we're chopping off part of the answer. And that is our answer on that one. So what if we're trying to check out and see if our cancellation properties are working or not? So here's one. Find each value. Inverse tangent of the tangent of pi over 3. So this is going to be okay as long as this number we're plugging in falls in between negative pi over 2 and pi over 2. And so does pi over 3 fall in there? Well, yes it does. It's bigger than negative pi over 2 and it's smaller than pi over 2. So that works. So we can use the cancellation properties. You don't need to write this out. When you're doing these problems, what you do need to write out is this to show me that you checked to make sure it was in there. Since it is that, then we're using that cancellation property and we get pi over 3. How about this next one? Does this next number, does what we're plugging into that fall into the proper domain here? Let's see. So positive 2 pi over 3 is greater than negative pi over 2, but it's not less than pi over 2. And so this one we cannot use cancellation on. So we're going to have to work it out old-fashioned way. So the tangent of 2 pi over 3, that would be an angle that's over here is going to be a negative number. It's going to have the same tangent as the tangent of pi over 3 had. And so it's going to have, other than being negative, it's going to be negative square root of 3. So now, what's the angle whose tangent gives us? What's the angle whose tangent was negative square root of 3? Well, choosing between quadrant 1 and quadrant 4, now we're coming from quadrant 4 for that, and we're going to get a negative pi over 3 for that. All right. So, the last thing we want to look at in this lesson is the graphs of the inverse functions for inverse cosecant, inverse secant, inverse cotangent. They are as follows. They're down here. And so here's the graph for inverse cosecant. This one's for inverse secant. And this one's for inverse cotangent. Now for inverse cotangent, it's running between 0 and pi, just like the tangent was. Just happens to be going the opposite direction. Instead of starting here and going up like that, it starts up and then goes down. Starts up close to pi and then comes down to 0. So it looks very similar to the inverse tangent function, but, and of course inverse tangent ran from negative pi over 2 to pi over 2, but still, nonetheless, it's got a similar shape, though flipped, just in a different area. On this one, it's not hard to follow. We can use any real number for our domain, and our range is going to go from 0 to pi, not including the 0 or the pi, because keep in mind this is a horizontal asymptote down here. On these, we end up with horizontal asymptotes. Now, on this, some books will use consecutive intervals, unlike ours. Ours is choosing to use the intervals that it does because it makes it easier when you're doing some of the calculations with inverse trig functions. It helps you out when you're trying to work out, wait, is that positive, is it negative? This just kind of helps to use these. And again, all of those domains and ranges, all those intervals are found over here on the bottom of page 1.